completely, so I think it couldn't, I think this topic could hardly be more different. So we go from gravity to statistical mechanics. So people here know quantum field theory, right? And do you know that? Do you know conformal field theory? Do you know what the Ising model is? And do you know that the Ising model is a conformal field theory at the critical temperature? Namely that it's scale invariant and it has power law behavior for correlation functions, and those power laws are governed by critical exponents. You learned about phase transitions. Okay, very good. So let's recap a few things. We have to review a few things before starting the paper itself. So the object that we are going to study is the two-dimensional Ising model, which is defined, very simple definition, where you have a lattice, a two-dimensional lattice. At each vertex of my lattice, I have a spin that can take two values, +1 or -1. At each edge of my lattice, I have a coupling, Jij. So this guy I have at the vertex, and this guy I have at the edge. And for us, this Jij will be the same for all edges, and it will be just J. And so we have a summation over all configurations, which are sets of sigmas that can be plus or minus 1, of exponential of minus the energy over time, over the temperature, and the energy is just the summation over all edges, I, connecting I and J, of sigma I and sigma J. So this is familiar to everyone, right? So everyone knows that this is just the Ising model, where I have some coupling, J, that tries to force the spins to be aligned with each other. Okay, very good. And so T is the temperature, and this is the definition of the Ising model. Okay. So now let me review a few things that were well known at the time of this paper, most of them. And not everything, but most of them were well understood at the time of the paper. And I think you probably have seen some of them, at least in some way. So now you can ask, what are correlation functions of two spins that are far away, sigma I and sigma J? If I and J are very big, the separation, much bigger than the lattice spacing. Instead of sigma I and sigma J, I can think of sigma at position R, sigma at position R prime, where R and R prime are much bigger than the lattice spacing. And then what is this correlation function, this expectation value of the spins between, which you understand how to compute, right? You just do the sum, that same sum with sigma I, sigma J downstairs divided by the partition function. And what is this correlation function? Well, it depends. There exists a critical temperature below and above which things change. So if you are before the critical temperature, if your temperature is very small, things want to be aligned. Because if temperature is small, that exponential is very big and it suppresses things that are not aligned. And so then you have order at low temperature. At low temperature, this correlation function is a constant plus an exponentially suppressed term. So when you go to very large distances, you ignore this exponential, and you get that this goes to a constant. And the constant is the expectation value of the spin. And this expectation value goes to 1 if the temperature is 0. because if the temperature is 0, you really suppress everything that's not aligned, and all spins must point up or down. But it's one, you break the symmetry, and it's either all up or all down. Then, as you increase the temperature, you approach a critical temperature, which actually you can compute, and it's given by some very simple expression, where the temperature over J is just this 2 over log 1 plus square root of 2. It's a known number. And this critical temperature, by the way, T over J is the only parameter that matters. So I write T, but of course it's T over J that matters. At this number, what happens is that this expectation value goes to 0. So now it's no longer true, and it goes to 0 with a funny power. That power is a critical exponent. And there, it's no longer true that I have this constant. Instead, now they decay, but there's a power law with some small critical exponent, 1/4. So now it decays, but it doesn't decay exponentially. It decays with a power law, which means that there is a critical theory. So this, at this point, we have a conformal field theory. Things are decay with a power law, and we don't have a gapped quantum field theory. We have what we call a gapless quantum field theory. What if we are above the critical temperature? Above the critical temperature, we have disorder. The spins want to be disordered. There is chaos, and things just decay exponentially. And now there is some exponential decay. There's also some power law dressing, but there is an exponential decay, and things decay very fast at high temperature. Okay, very good. There's also a relation that you can write Z as something related to fermions. That's one way of solving the 2D Ising model, is in relating this partition function to some partition function of some free fermions with some gap. If you have never seen that, it's just an observation. At the end, if we have time, I might tell you a little bit about the connection between that, but that's one of the ways of solving the Ising model, is in relating this partition function to a partition function of some fermions that you can then solve exactly. And in particular, those fermions become massless fermions at a critical temperature, and that's the conformal field theory. It's a theory where the Lagrangian is just some fermion of 0 mass. Okay, that's the theory that describes this model in the continuum. But if you have never seen that, ignore this connection with the fermions. And our goal is to study this theory, this very important statistical mechanical theory. Yes?
The theory is only conformal exactly at TC?
Yes, only at TC. Before TC, there is a mass, and that mass, that correlation length, explodes as T goes to TC. So if you are close to TC, you will have, for example, domains of upspin of a typical size. That typical size becomes bigger and bigger and bigger as you approach TC, and you get scale invariance at that point.
My question is, this formal behavior is not exactly at TC, but near TC, because at TC, I think it should be constant, the correlation function. I mean, it's my intuition. I'm trying to understand this. Because for me, it does not look scale invariant if the correlation function behaves.
No, that's what it means to be scale invariant, because you see that whenever you have an exponential like this has some dimensions. So this kappa is a mass. It has units of 1 over dimension. So this is not scale invariant. It requires introducing a scale. This has no scale here. This is just a theory that if you plot, it just tells you that if you multiply the distances by 2, this changes by 2 to some power. But if you look at the plot, you cannot tell where the scale is. You just see some power law. When you see a power law, you look at the power law and you try to say what units are in the x-axis, and you don't know. Because the power law looks the same if I rescale. So that is what we mean by saying it's scale invariant. If you go to the Ising model at the critical temperature, and you look at regions of up and down spin, you don't know at what scale it is. You have a bunch of black and a bunch of white. and you zoom in, and it's the same, and you zoom out, and it's the same. And you cannot tell at which scale you are. That's because if you compute correlation functions, they have these power laws, and power laws are invariant under scales. You rescale things, and it's the same power law. So being scale invariant doesn't mean it's constant. It means this. Yeah. Yes. 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 You can think of it that you start with a CFT, which is a gap theory, and you could imagine how do I go from a theory without a scale to a theory with a scale, and you can do it by starting with a conformal field theory, perturbing the conformal field theory, and letting it flow. And then it will flow to these gap theories. And depending on the sign of the perturbation, it will flow to this phase, which is ordered, or to this phase, which is disordered. Very good. There is another thing that I want to review, that if you solve the 2D Ising model, some of you probably saw the exact solution of the 2D Ising model, but maybe most of you did not. But maybe what you saw is this high temperature, low temperature duality, this Kramer-1S duality. So let me review that. That's also important. So Kramer-1S duality. And basically, let's first start with the observation that this partition function that we have here, this z, I can write it in the following way. I can describe my configurations of spins by saying that some spins are up, some spins are down, and drawing the boundary between the regions of up spins and down spins. You agree that if you draw the boundaries between up and down, you are giving me the full configurations. You just give me one up spin, and then you draw the boundaries, and you give everything. Now, or more precisely, if I have my lattice, just to be a bit more careful, this is very schematic here, this is in the continuum already, but if I am in the discrete, this boundary would be something like this, for example. And that would mean that inside the spins are up, outside the spins are down. Right? So these spins here would be up in this example. And then you can say that my partition function would be a summation over these loops that separate up and down. These loops are in the dual lattice, because you see these are loops that the vertices are in the faces of the original lattice. So this dual lattice is the lattice where faces of the original lattice are swapped with vertices of the dual lattice and vice versa. Right? So a vertex of this red line was a face of the original lattice, and similarly, a face of this red lattice was a vertex of the original one. Right? So that this is the usual dualities of lattices, that you replace faces and vertices. And clearly, we can write that summing over configuration is summing over loops of the dual lattice. And what's the energy now? Well, the energy now is, now there is an energy when I transit, the boundary of this is e to the minus, let me write the expression and then you see if you agree, e to the minus 2j over t times the length of the loops. Let me explain what I did here. I'm not finished with this expression. I just said, suppose all spins are up. If all spins are up, I get some constant. This is all up. And now I start putting blobs. What's the difference of energy because the blobs are there? Inside, all up or all down is the same, right? -1 times -1 is the same as +1 times +1. What matters is at the boundary. At the boundary, instead of e to the minus j, now I get e to the plus j. And so compared to all down, I have to pay this factor in my partition function. Sorry, I did a mistake here. This is the Ising model. It's e to the minus beta times the energy, and I want this. So now you agree with this expression, right? So the difference of up versus up down is twice that term up there. And so this expression is correct. Do you agree? So that's an expression which says that the Ising model, you can think of it as a soup of loops. You just sum over all possible loops, and the action is the length of the loop. Okay, good. So it's a gas of loops. Okay. On the other hand, so this expression you see, replaced spins. Instead of thinking of spins, now this got replaced by domain walls. We went from the original degrees of freedom that were spins to these walls between ups and downs. Okay. Very good. So this is one way of writing the Ising model. Now let me tell you about another way where we also write Z as a summation over loops. But now this will be loops in the original lattice, not in the dual lattice. Okay? So let's find that other way of thinking about the Ising model as loops. And that's very easy. So you just do the following. You just remind yourself that you have the following identity. So you see that this exponential, I can write it, let me write an equation, and then we see why it is obviously true, is cosh of j over t plus sinh of j over t sigma I sigma j. Why is this obviously true? Because this only takes two values. It's exponential and exponential with minus sign, because this can only be 1 or minus 1. So I just need to check that when I put 1, I get cosh plus sinh, which is exponential with plus. When I put minus 1, I get cosh minus sinh, which is exponential with minus sign. So this is a true statement. And therefore, this true statement, this is equal to cosh of j over t times 1 plus hyperbolic tangent of j over t sigma I sigma j. And so you see that this would be one term, this would be another term. And now, in our partition function, we had a product over all links of this exponential of j over t sigma I sigma j. So for each lattice side, I have a product of terms like this for each link. And so when I open up the parentheses, I take either 1 or 2. Do you agree? So I either take 1 or 2. But then, you see that basically, suppose I take 2 for this link. So this yellow means we take 2. And white means I take 1. Now, suppose I took white for everyone and 2 for this link. And then I do the sum over spins. But the sum over spins of sigma is 0, because sigma and minus sigma gives 0, because I have 1 and minus 1. So this configuration, when I bring down, I have sigma at this cusp and sigma at this cusp here. I get 0 when I sum over. So the only way I don't get 0 when I sum over this is to use, for example, this link. Because now this sigma appears twice. It appears as sigma squared. But then I still get 0 because this guy appears once and this guy appears once. So not to get 0, I must always form loops. Right? And now each sigma appears twice. Sigma square is equal to 1. And therefore, I can just ignore all the sigmas and say that my result is just hyperbolic tangent of j over t to the power of the length of the loops times an overall constant that I put outside. And so here are two expressions, two representations of my partition function that are the same, it's the same object, which describe the model as sum over loops, one in the dual lattice, one in the original lattice. Right? Okay. And now, and now you see that you have these two expressions. And this one expression, this expression here, this weight goes to 1 as t goes to 0, and goes to 0 as t goes to infinity. Whereas this one is the other way around. It goes to 0 as t goes to 0, and to 1 at t going to infinity. And so one representation is good for low temperature, one is good for high temperature. And the two get swapped. When I swap low and high temperature, I swap a big weight in one representation, becomes a small weight in the other, and vice versa. And so you see that when all the weights are 1, it means that in that case, all loops are weighted equally. And if all loops are weighted equally, it means that loops can proliferate. I can have lots of loops. There's nothing suppressing loops. And so that's what we see. When the temperature goes to infinity, I have lots of domain walls. That's my intuition. That's correct, because then I expect spins up and down to oscillate like crazy, and there are domain walls everywhere. On the contrary here, when t goes to 0, I have lots of loops of spin. Because when t goes to 0, all spins want to be up. And so here, when t goes to 0, spins up proliferate. And here, when temperature goes to infinity, domain walls proliferate. And so this suggests that there should be a duality, a way of thinking of spins and domain walls as objects that not only the partition function has this duality, but there should be an object which is related to these domain walls that realizes this duality between high and low temperature. Okay? And this object, if this spin is related to this spin object sigma, these domain walls will be related to a new object that we will define, which is mu. And this object is going to be called the disorder operator. And the main result of this paper, that's one thing that I think is really quite unique about this paper, is that the main result of this paper is a definition. If you want. It's not a computation, it's really a definition. It shows really when sometimes if you have the right definition, then you just follow your nose afterwards and you are led to the right physics. And here the definition comes hinted by this picture, that you have on the one hand spins, on the other one domain walls. And the two regimes look very different at first sight. You have order in one case, disorder in the other. But then this picture starts to say, maybe things are not so different. Maybe in one case, I have proliferations of spins up. And that's like spin condensation. And in the other case, I have proliferation of domain walls. And then I have domain wall condensation. And then that gives me another way of thinking of disorder. Disorder might be order, but of a different order parameter that I'm not so used to think. Normally I think magnetization. If there is a big chunk where the magnetization is up, I say it's ordered. But I don't think of if there is a big chunk where there are lots of domain walls, that's ordered as well. But this definition leads to thinking of this, gives us now the possibility of thinking, if we want, of new order parameters that measure disorder in the same way that the conventional ones measure order. That is when the weight goes to 1. When the weight goes to 0, it's the opposite. It says that now we want to suppress loops. So when the temperature goes to 0, we want all spins to be up. So we want no loops at all. And similarly here, when the temperature goes to infinity, when the temperature goes to infinity, we want no loops of these spins at all, and we want total chaos. As you tune the temperature, there should be a critical temperature, because we have this disordered phase. If you want, it's experimental. We have the disordered phase, we have the ordered phase, and in the middle there is a transition. How do I see the transition again? I look at pictures like this of spins up and spin down. When I am in the ordered phase, there are huge regions that are black. When I am in the fully disordered space, everything is up and down. It's totally gray. When I am at the critical temperature, there are regions of all sizes, and I cannot tell at which scale it is. I cannot go and say this is 1 centimeter. That doesn't work if I am at the critical temperature. I look at the picture, you zoom in by 10 times, the picture is the same. You zoom out by 10 times, the picture is the same. That's what it means to be scale invariant. That's the critical temperature. Okay? So this is at Tc. So that means that there is a weight, if I call this x, there exists an x critical where this partition function has a critical point. Right? But similarly, if I call this weight x tilde, there exists a critical value where this partition function is critical. And they should be the same. So if I equate x tilde of t to be equal to x of t, that gives me a critical temperature. And so if you do tangent hyperbolic equal to exponential, you solve for the temperature, you get that expression that I wrote there. And that's how you derive the value of the critical temperature of the Ising model. If there is a, so it's not really a derivation because it's the following. So this just tells you that you could have the following. You could have order, then a critical temperature. You could have disorder, and another critical temperature. And then you could have a new phase. This would also be compatible with this scenario, that you could have 2 critical temperatures. But if you know there's only 1, then they must be the same. Then you can find it by equating these weights. So if this phase is not there, then you impose that this is equal, and this tells you that T critical is this J divided by log 1 plus square root of 2. Okay, that expression there. Okay, so this picture that we go from spins up everywhere to domain wells everywhere leads to the picture that in the same way that we have sigma I, we would like to think that under this duality, not only the partition function can be related at low temperature and high temperature, but there should be a new object, mu I, that if you want is the dual of the spin. And this guy should be related as this is related to spins. And this guy should be related to domain walls. Right? And the question is, what is this definition of this object? And that's what this paper solves. Okay? Any question here? Okay. So in the same way that I can define my operator sigma by defining what are correlation functions of sigma, right? I just say it's summations over all the sigmas of, I put sigma I, sigma j. Right? This is the definition. The idea is similarly, let's define what is mu y, mu j. Let's give a definition that defines my operator. The definition is the following, and it might look a bit weird, but that's the definition. So let's define and then see that this definition makes sense. The prescription is the following. Take the partition function, divide by the partition function, like here, with some weights jij. But in the numerator, put the partition function where the weights are now j tilde ij, where the prescription for this j tilde is the following. You have your lattice, and you define the mu's to live in the dual lattice, for example, here and here. So this is the index I lives in the dual lattice. And now draw a path that connects I and j, for example, this path. Now look at the edges that cross this path. This, 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 this. Right? So these are the edges that the path gamma cross. Right? And then in those edges, flip for those edges jij replaced by minus jij. And that's the definition of this j tilde. J tilde is the same couplings except at those edges you flip the sign. Okay? So this, okay, yeah. In the edges that the path cross, j goes to minus j. In the edges that it doesn't, it's untouched. And so this definition depends on a path gamma that connects the two. Right? Given some path and some points I and j, this is the definition. Okay. Now, important results, so claims. A bunch of claims. One, this is gamma independent. It doesn't depend on the path. That's crucial, because then I can say it's a local operator at point I and at point j. It's not some snake that depends between I and j. It's really something at I and something at j. Okay, very good. Are you after soft matter? Yeah. Soft matter is at Principia in Pamplona.
Oh, all right. So I'm just going to be here, right?
Yes.
Okay. All right.
That's what I was told. I suspect so. Ask, please, outside. I don't think so. But, okay. So claims, it's actually gamma independent. Second claim, moreover, this correlation function mu of r prime is actually exactly equal to the sigma expression there at the on the right with high t swapped with low t. So not only it's really the same, it is like sigma, but if I replace this sigma, if I put mu here, I should go here and put a bigger or equal here and a smaller or equal here. It really behaves like sigma, but in the opposite phases. Namely, it has an expectation value at high temperature, and it decays exponentially at low temperature. It behaves like this expression. It's really the dual of this expression. And actually, we will show this claim by showing point 3, which is that the sigma correlation function, sigma I, sigma j, whose definition is the usual one, that I compute the average by computing expectation value of this object, is actually also given by a ratio of partition functions. One of them is just the original partition function, and the other one is one where I change them. I change the coupling, and the change of the coupling is now as follows. Like before, I say I have a point I, but now I is in the original lattice, and I have a point j. I draw a path. That's a path gamma. So I could say this definition depends on gamma, but then, of course, we will show that it's actually gamma independent as well. Because, of course, we know this doesn't depend on any paths. This is just a new definition. And we would go to this path, and now, along these lines where the path is, Jij over T would go to Jij over T plus I pi over 2. Okay? So I would change, and otherwise, at these points, I don't touch J. So the claim is that these two objects can be defined in this way. Define some paths and change the couplings along the path. In one case, you really change along the path. In the other case, along the edges that the path passes by, because it's in the dual lattice. But otherwise, very similar definitions. Okay? Good. Okay, so I would like to establish these claims now. Any question here? Is it clear so far? Am I going too fast? Do you want clarification on any of these points? What should I erase? I think I will erase this part of the sum over loops. So no question here on this sum over loop stuff? Both are clear? Yeah? Okay. Okay, so how do we see it's independent of the path? Is it obvious for you that it's independent of the path? That this definition, take 2 points, I and j, draw a path between them, and change the couplings in the lines that this path passes by. And now I say it doesn't depend on the path. Can you see why? Can you tell me why? What's the argument? Why this doesn't depend on the path. So take another path, imagine another path. And the claim is that it doesn't matter. So let's draw 2 paths. So one path could be this. The other path could be, for example, this. Okay, so here are 2 paths that connect I and j, right? And the claim is change the signs in the lines that the path pierces. So in one case, change here, but then the two paths tell you to change in different places. And both paths tell you to change here, right? But the lower path will tell you to change here, and the upper one will tell you to change here, for example, right? Now, why would these two paths be the same? Can you see? That's not enough. That's not enough. So notice something. Let's notice that these paths, the difference is some closed region here, right? So inside this region, how many spins are there in this picture? In this example, inside this dashed line, how many spins are there? 4, right? So there are 4 spins, one here, one here, one here, and one here. So there are 4 spins in this case, right? With a bigger domain, there will be more spins. And so let's suppose we flip sigma I to minus sigma I inside this dashed line. Right? Now, this does nothing because I sum over sigmas. So relabeling sigma to minus sigma is just a dummy variable, right? The partition function, I sum over all spins. So if I decide in some domain to change sigma to minus sigma, that's nothing. I sum over it anyway. Do you agree? So flipping the signs inside this region is nothing, does nothing. But if you flip the signs inside the region, inside, it doesn't matter. Up, up is the same as down, down. But at the boundary, flipping the signs at the boundary, flipping all the signs inside, so first we agree that this is nothing. Because sigma I is just dummy. Right? It's just a dummy summation variable. But on the other hand, this is the same as change j to minus j at the boundary of the dashed region. Because at the boundary of the dashed region, what I'm saying is that at the boundary of the dashed region, there are some lines that pierce it, right? And by flipping sigma to minus sigma, we flipped this guy from j sigma sigma, it became j sigma minus sigma. Because one sigma is inside, one sigma is outside. So the one inside got flipped. Right? So the conclusion is that changing the couplings j to minus j in a closed loop does nothing. Because that's the same as changing all sigmas to minus sigmas inside, and that's just a change of coordinates. So changing spins in a closed loop does nothing. Is it correct? Do you agree? So the conclusion is that flipping j to minus j in a closed loop is nothing. Because it doesn't change the energies at all inside or outside. And at the boundary, it changes. But that's just the same as flipping sigma to minus sigma. So it does nothing. Well, but then we are done. Because what's the difference between these two configurations? I start with the bottom configuration. And I change the sign in all the ones in the dashed line. But then I go to the other one. Right? Because in the yellow one, I had changed this sign and this sign. But in the dashed, I change it again. So I undo the change. So by changing all the signs in the dashed line, I remove the signs that I had changed here and put them here. So by this, I can change any contour. I can deform contours from one to the other. because contours differ by these closed regions. Right? So if you have a contour, you can deform it. You can go and deform it, and deform it more, and deform it to whatever you want. Right? Because the difference between contours is always this closed lines, and the closed lines don't matter. Sorry? No, this, I went from this line, I deformed it to this, I deformed this gamma to this gamma, right? And now if I want, I can deform a bit more, and I can deform to this contour. So all these paths are the same. This path gamma differs from this path gamma by, again, some closed region here with this Tetris shape. You agree? So flipping the signs in this line and flipping the signs in this line is nothing. And so I can go from flipping the signs here, I add flipping the sign in both, and that cancels this and puts it here. Sorry? We showed what we wanted. It's path independent. That's it. So if there are two different paths. So right, because you say I pick a path, and I say, okay, change the couplings j to minus j on that path plus on a closed loop, because the closed loop does nothing. But if you change on a path plus a closed loop, you add the path plus a closed loop, you change to another path. And so then you can relate paths to other paths, and therefore it's actually path independent. It's a topological argument. It assumes that I have 2 points and I can deform the lattice. If I put my lattice on some funny topology, like some torus, or if there are impurities, then things could change a bit. If I remove a part of my lattice, now I could have different topological contours, ones that go below the hole and ones that go above. And then we would say the ones that go above the hole are all the same, the ones below the hole are all the same, but the hole is the hole. The paths are different, the ones that go below and above, right? But topologically, if you can deform, it is independent. Okay, so we check this, and of course, it's modulo topology. I mean, if there is some funny topology, then it could depend on some topology. Okay. Now, before we establish this, before we derive this result, let's see why it looks correct, why it looks plausible. Okay, let's see why it is plausible. So let's check, let's do not 2, but 2 prime, which is just check that, do some checks. Let's see why it's possible. So for example, suppose you send t to infinity. Then j over t is equal to minus j over t. It doesn't make any difference to change signs. Do you agree? And therefore, what's the ratio of this guy over this guy? 1. And so we conclude that when t goes to infinity, this mu mu goes to 1. That's exactly what happened here when t went to 0. And so now we see that for mu mu, instead of 0, it's that when t goes to infinity, that this guy goes to 1. Okay? Okay, because what we want to claim, let me already write here. Let me see what, let me write in red. We want to say that mu of r prime will be now that here there will be, instead of sigma, there would be mu. Instead of t smaller than tc, there would be t bigger than tc. Instead of t going to 0, it would be t going to infinity. It's then that mu square goes to 1. Okay, so that's plausible. Already we see that that makes sense. Moreover, at t smaller than tc, we know that the sigma I wants to align. They want to all point up, right? And therefore, if I have this domain wall, I and j have some path gamma, this guy, there is some energy which will be the length of gamma times 2j over t, because I flip the sign of all the lines that appears here. Right? And so there is an energy cost that grows with the length. Right? And so we have this being some tension, or if you want, some string tension. And therefore, the correlation function of this mu mu, when I am at low temperature, should behave at low temperature as exponential of minus that string tension times the length. Okay, but that's exactly what we see. If we were to go here and say that at T smaller than Tc, at low temperature, it should be some exponential decay. And that's indeed what we start to see for mu. Okay, so it starts to be plausible. So things are at least reasonable. Okay. Good. So actually, to prove this, it's not complicated. It will follow easily once we establish 3. So you have to believe me now that once I establish 3, then 2 follows right away. We just need to show to bring sigma and mu to the same footing. Mu was defined as some path. Sigma is not. So let's write sigma as a path, and then that the two are the same will become obvious. Right? So that's the idea. Okay, so we want to write sigma. Sigma is written here, and I would like to write this in a definition like this. Namely, I would like to write this as that ratio there. Okay? So I want to write this as a ratio, as this ratio, a star. Okay, so let's try. And it's actually very easy. You just notice the following. You just notice that I have this downstairs, sigma I, sigma j. And then I have, so here is sigma I, and here far away is sigma j. Okay. And now I'm going to do the following. I'm going to write that this object, sigma I times sigma j, it's equal to sigma I times sigma squared times sigma squared times sigma squared times sigma j. This is obviously true because this guy is equal to 1, because sigma squared is equal to 1. Where what are these sigma squares? They are the sigmas along some path that connects them. Right? So these are the sigmas that I put along this path. So here I've done nothing, I've just inserted 1 a bunch of times. Right? Okay. But now I use the fact that if I have sigma I I prime, where these guys are connected by a link, like this. E to kappa sigma I prime. This expression takes two values. It takes exponential, and it takes exponential with a minus sign, or with a minus sign in front and a minus sign upstairs. So you see that you can write this. It's nice if I put an I here. This I is square root of minus 1. You can write this as exponential of k prime sigma I prime, where k prime is k plus I pi over 2. Look how it works. If the product is 1, I get e to the k prime. K prime is k plus I pi over 2, so I get exponential of k times exponential of I pi over 2. That's the I that I put here. What if the product is minus 1? Then I want to get minus I times e to the minus, but that's what I get, because I get e to the minus k and e to the minus I pi over 2, but that's minus I. So yes, this is true. Do you agree? Okay, so I'm done, because now I have this sigma I, sigma j. I wrote it like this, which by putting a bunch of ones, but this is nothing but multiplying sigma at this link times sigma at this link times this link times this link, right? I just multiplied a bunch of links. And for each link, I have these sigmas and the corresponding exponential in the weight. And all I'm saying is, along that path, change k to k plus I pi over 2. Does it depend on the path? Of course not. I mean, we just... it's my choice. You could pick another choice. Of course, the result doesn't depend on the path. Okay? And so this is true. You agree? I can just change j to j plus I pi over 2 and do it along any path, and it's path independent. Okay? So we checked. This is true. This is true. This is true. Okay? And so now we have two different maps. We have that mu and sigma are given by similar expressions. So we have sigma equal to some z over z involving some map j to j prime, whereas mu is equal to some z over z involving some map j goes to j tilde. Otherwise, they are the same. But in one case, you flip the sign along the path. In the other case, you shift by I pi over 2 along the path. Okay. And then, there is the following very simple observation. So the key observation now. Is the following, is that you have this map that flips, I define this k, right, which is j over t. We have these two maps. One map is k to minus k, and k goes to k plus I pi over 2, right? And then you can ask what happens to this map under this Kramers-Wigner duality. That is a map that flips j over t to a function of j over t such that this exponential and tangent are swapped. Right? So it's you can easily find the map. You see what I mean, right? It flips the weight which was tangent hyperbolic to the weight that was e to the minus 2j over t. In other words, this function f is minus 1/2 of logarithm of hyperbolic tangent of j over t. So if I replace j over t by this expression, e to the minus 2j flips to tangent, and tangent flips to e to the minus j over t. So this is this function f of j over t. And now you ask, and this is of course k, and so this is k. And you ask, what does this map do? If this k, what does it do after I apply this duality? And now you see, for example, k to minus k. Tangent goes to minus tangent. So log picks an I pi over 2. So this change in the other regime becomes k goes to k plus I pi over 2. What about k goes to k plus I pi over 2? That flips tangent upside down. But tangent upside down flips the log. So the other one flips k to minus k. And so we are done. We just showed that the two correlation functions, once we swap low and high temperature, they are exactly the same. And therefore, this statement that I wrote here, once I finish putting the bracket, is a true statement. Okay? And so now, you see, we have a new way of thinking. We have this non-local object that is defined by this path, that in fact is a local object. It's a correlation function of local operators. And that gives us a new way of thinking, that now we can think of disorder in pretty much the same way as we think of order. Order is the condensation of spins. Disorder is the condensation of domain walls. So it's a powerful definition that allows us to have now new order parameters to look for new phases of matter in condensed matter. So it's truly a very powerful result. And many of the recent dualities that people have explored in condensed matter in modern times are extensions and generalizations of this to more complicated statistical mechanical models. Yeah, I can't help but say one thing. So now, all we have discussed these objects where we have a spin at the vertex, right? We have spins that live at the vertices, sigma. And we could imagine, and we also have mu's that live at the faces, mu. And there is a nice object you could consider now, which is, instead of considering sigmas or mu's, consider this bound state, if you want, of sigma and mu. Think of these guys together, a sigma and a mu. It's a fun object because it has some orientation. It can be like this, like this, like this, like this. Okay? And just like fermions have different components and so on. And indeed, this object is the fermion that I told you about. So the fermions, and you can indeed check that this object, just based on cartoons of changing couplings, you can check that it has exactly the fermion statistics and it obeys all the equations that you expect for a fermion. And that's one way of getting to the fermions. Okay. Okay, good. So that's it about this paper. So I'm done. And like I said before, I think it would be nice if someone would give a short presentation about one paper that refers to this paper that is a relatively modern paper. And it should be like aimed at 10 minutes, aimed at explaining one modern idea, so that by seeing it, we get a glimpse of, there was this paper from the 60s or whatever, maybe 70s, from 70, exactly 1970, and here is a paper from 2010, 40 years later, and we get some glimpse of the kind of impact that this paper had, which was huge. So would someone like to volunteer to give a 10-minute presentation on some paper that refers to this paper? No, same thing, Tuesday, 10:30 a.m., The first 20 minutes we reserve for a student presentation, and then I discuss the new paper. Okay, very good. So you can tell us a little bit about some statistical mechanical paper next week. Very cool. What's your name again? Sorry. Marvin. Okay, so Marvin will tell us about some paper that works with disorder or something like that. Very good. Thank you. I don't know if you have questions or. I don't want to change because they are chronologically ordered. Why would you like to change?